Hello, this is Mrs. Hedden. This is Chapter 15, Notes 1 on Thermodynamics. These notes deal with efficiency, and there is one worked first law of thermodynamics with efficiency problem. Efficiency is simply a way of representing how much energy has leaked out of the system. We've always talked about loss of energy due to friction. Now we're just quantifying this loss by looking at the heat escaping from the system. The general definition of efficiency or formula is efficiency is equal to work out divided by the energy in. The energy in can come from all different sources. You could be doing work, force times distance. You could be having heat being transferred in. You could be having calories transferred in. We could have a change in our internal energy because of eating food, or a change in our internal energy because of heat coming in or heat escaping. The heat escaping would be workout. All right, so that's efficiency formula. Efficiency has no units since the units of energy cancel. That being said, you must be careful to have everything in the same units. Both our work out and our energy in have to have the same type units, be them joules, kilocalories, or calories. Energy is always lost. There is no way that efficiency can be greater than 100%. In fact, except in the ideal world of problem solving in physics, it never reaches 100%. Some typical efficiencies would be like a solar panel is 75 to 80% efficient. Automobiles that run on gas is about 25 to 30%. Diesel's a little better, maybe like 35 to 40. Automobiles that run on electricity is 70%. Coal power plant is about 35%. Natural gas is about 45%. And our bodies are approximately 25%. Now bear in mind these numbers I pulled off the web very quickly today. Many of them are very political. The nuclear power plants had efficiencies ranging from 30% to 90%, depending on what website I looked at. And there was no way I was going to use any of those numbers because there was too much of a disagreement. I tried going to reputable sources, but again, take these numbers with a very large grain of salt. For example, an electric automobile looks wonderful, but it does not take into account the efficiency of converting some fossil fuel or some fuel, whatever it may be, into electricity first. So these numbers are just some ideas for you to go and take a look at. Our first problem, and our only problem for this notes, is how much food energy will a man metabolize in the process of doing 35 kilojoules of work with an efficiency of 5%. And then, how much heat transfer occurs to the environment to keep his temperature constant. Well, we write down our knowns. The efficiency is 5%, which is equal to 0.05. The work out is 35 kilojoules, and we've got some efficiency. In this case, we're talking about metabolizing energy, so we're talking about the change in the individual's internal energy. So instead of saying energy in, we're saying delta U. So delta U is what we're hunting for. And then it's just plug and chug, and we get delta U equals 700 kilojoules. But because we're talking about metabolizing food energy, it makes more sense to express it in units of kilocalories. So a kilojoule, as opposed to a joule, there's 1 kilocalorie is equal to 4.186 kilojoules. And that gives us the change in food energy, 167.22 kilocalories, in order for him to do 35 kilojoules of work. The second part is then asking, well, how much heat transfers to the environment to keep his temperature constant? Well, since we're talking about the energy that was leaked out or lost to the environment, if he uses 5%, that means he didn't use or lost 95% of the food energy. And so we're assuming that that loss was eventually due to leaking out. So the Q lost is simply 95% of whatever he metabolized. And that was 167.22. So the Q loss is 158.86 kilocalories. And that's the end of this problem. Thank you very much for your time.